Okay, we got the recording going. Okay, so last time I just barely introduced the slightest little thing about section 3.2 arc length. And so, yeah, the big question is going to be if I have a curve, like this, and I want to compute how long is that, as a curve in space, what's the total length? How would I do it? Now, the big picture is what I'm going to call typical, in that we're going to take a question that we don't know how to understand very well. We're going to chop it up into little pieces, right? Just like in every single variable calculus example that you've ever seen. Take a hard problem, chop it up into little pieces, and then study the small pieces individually. And so, how do I find how long is this little piece of curve right there? Just that one little piece of curve. So, all right, well, that's something we're going to have to look at, and here's the details there. If your curve is floating along like that, here then is a little piece of curve. And you'll notice that it is approximated by the position differential, dx. And keep in mind what that is now. That's our linear approximation to change in position over the amount of time that it took us to get across this little piece of curve. In other words, we were here, now we are here. Right? But while we're at this first point, we don't exactly know yet how the curve is going to curve, but based on the direction we're going and the speed, etc., this would be our linear approximation of our change in position. So it's the differential, not the increment, right? It's approximately correct, but not exactly. So, so you make this realization that the ds that we're interested in is just the magnitude of that dx vector. So now we need to understand the dx vector. What's the dx vector? Well, this part is actually pretty believable. Dx is x prime dt, right? You can view this as an interpretation of the chain rule, or you can also view this as just an interpretation of velocity, right? Displacement is velocity times time. Right, it's a very fundamental notion about interpreting. In fact, what does velocity even mean? Well, it means this. Right? Okay. All right. So now the next thing I need to talk about is this unit tangent vector, which we have not previously discussed. The unit tangent vector, just like I have it drawn here, is the unit vector pointing in the direction that the curve is going. Namely, it's the unit vector pointing in the direction that the displacement vector is pointing. Which, by the way, is also the same direction that the velocity vector is pointing. Right? So, in fact, if I were to draw the velocity vector on here, it would be something like that. Here's your velocity vector, for example. So, so how would I compute this unit vector in that direction? Well, it's a unit vector in the direction of vectors that I know. And so the easy formula to write down for what that unit tangent vector is, just take any other vector pointing in that direction. For example, perhaps the velocity vector, aka x prime, right, divided by its own magnitude. And there you go. There's your unit tangent vector. How are we doing? Is everybody on board? Okay, so that gives us an alternative way to write this formula that we had over here. We previously observed that dx, the thing whose magnitude gives us the ds, the arc length that we're actually interested in. That dx vector, I could also interpret it in terms of the unit tangent vector, and it turns out that it's just TDS. And why is it TDS? Well, there's any number of different ways to see this. I'm going to make the most geometrically natural one, I think. And that is, we have a unit vector and a magnitude. Right? And if you know a direction and a magnitude, that defines a vector. Right? So the dx vector, well, its direction is the direction of t. The unit vector defining that direction. Its magnitude, what's the magnitude of the dx vector? Well, the whole point of this discussion is the magnitude of this dx vector is the ds scalar. Right? So this is just straight up interpretation of dx as a vector with a magnitude and a direction. Boom, TDS. Okay. You can also connect these algebraically. Also perfectly fine. Okay. So that's the setup. And now it's just a matter of computation to see what we actually get here. If I want to compute the total length, that total length is going to be the sum of a bunch of little pieces of length, and we got a bunch of little pieces of length, like this. ds. We just argued over here that ds is magnitude of v times dt. Right? And we're done. We have ourselves a formula. This is a single variable calculus problem at this point. It's just do that single variable integral. Okay. All right. So, so let's, by the way, a quick digression before I move along. This unit tangent vector here is going to come up very significantly later on when we're in chapters 6 and 7. It's not going to show up very much in chapter 5 that we'll be doing before that, but that's going to be a big deal later on. Okay. All right, so let's do an example. Let's compute the length of here's a parametric curve. All right, I got a range of values of t. X and y are functions of t. That traces out some curve. Who knows what it looks like, right? And formula for length, arc length, is that. I do have to know what the velocity vector is. Well, the velocity is the derivative of the position vector. So there I'm just taking the derivative of each term. Time derivative, of course. Right? And how do I take a magnitude? Well, okay, so magnitudes are square roots. Unfortunately. Right? And so all I've done is plug in, just plug and chug. Well, I've done the plug. I'm going to leave the chug because this is a pretty nasty integral to compute, and I don't want to. Right? And unfortunately, this is a common plague on when you're trying to compute arc lengths. Very often you get ugly integrals. Big surprise, because you can see right here, it's always going to be an integral of a square root. And those are notoriously annoying at best, right? I mean, every so often you might get there might be some trig substitution you can do or something like that, but they're usually really ugly. Okay, so this opens up a new possibility for what we're going to call a reparameterization of a parametric curve. The first thing I want to point out to kind of segue into that as a concept is that every curve actually has lots of parameterizations, right? So it's easy to forget, right? I mean, usually we would talk about a curve as having an equation. It's the graph of a function, right? But we can't talk about the parameterization because there really are very different parameterizations of the same curve, such as, for example, here's a nice innocent-looking equation describing a curve we're all familiar with. And you can confirm that this is a parameterization because, after all, x squared is indeed y, right? It fits in the equation. So this is a parameterization of that curve. But at the same time, so is this, right? This, if this were x, and if I were to square it, then I do indeed get y. So this also is a parameterization, same curve. Right? So, there's lots of parameterizations. In this case, and let me stop short of always, but usually, right, typically, when there are when you're looking at two parameterizations of the same curve, the parameters are themselves related. And you can see very easily here what the relationship is here. T is been replaced by q cubed plus q. Right, and I've designed this example to be visually clear. Right. And again, that won't always be so immediately obvious. Geometrically, the idea here is that, all right, well, pick some point on the parametric curve, there's going to be a value of t that gets you there. But given that value of t, right, there's also a value of q that gets you to that same point. After all, these are both parameterizations of the same curve. So there's some value of q that gets you there too. So for a given t, there is a corresponding q. And vice versa. Right? So algebraic relationship between the parameters. Okay. So all I'm going to observe here then next is that I can make an algebraic relationship involving a parameter. And that will reparameterize the curve, and the algebraic relationship that I'm going to write down is that of arc length. So specifically, given a we're going to nail down this point as being the starting point. That's where t is equal to 0. So we're going to start from there. Well, wherever I might happen to be, whatever point I might happen to be at a particular time, I can talk about, well, okay, at that time t, I'm at that location, and I have therefore traveled what distance from my starting point? And of course, we have a formula for how to compute that distance. Well, this is explicitly an algebraic relationship between s and t. And so I can talk about, I like to think of a road trip in this circumstance. So imagine this is a road that you're driving along, and well, you could drive fast or you could drive slow. There's lots of different ways that you can drive along that road, right? Those are all effectively different parameterizations. And you can define your location by where am I at a particular time. But you can also, and this is a standard thing, you can define your location by how many miles have I driven. Right? You'll see this in the form of mile markers on the side of the highway. Right? There's always on I don't know if it has to be an interstate, but the freeways that are go cross country and stuff. There will be mile marker 165, and then a mile later is mile marker 166, etc. Right? And so you give me a mile marker number, that defines a location. So we have position as a function of a new parameter. Now it's just distance. Yes?
So is the tower there? Is that just like the name?
That's an awkward little reality. I mean, great question, by the way, and I was going to get to that next. We know we're supposed to be taking an integral of velocity's magnitude times time. It's just that the problem is that I've used t already. I've used t to represent the endpoint. Right? T is, because I want to know distance as a function of time, so this needs to be t. Right? But now as I look at as I add up, as I sort of, move along between 0 and t, what am I going to call the thing that takes on all of those values? Well, I can't call it t, because t is already fixed. It's the endpoint, fixed for the purposes of this calculation. So all this tau it's just, what we call it, dummy variable. It's just a placeholder, and you could call it sigma or aleph, or knock yourself out, right? And it's just a placeholder. Nothing to sweat over. Yeah, does that make sense? Mm-hmm. Yeah, but very importantly, though, you cannot call it t. Basically anything but t. Probably shouldn't call it s either. So, other than that, anything you want. Okay. All right. So, so once you have that relationship, once you have an algebraic relationship between s and t, all right, then, plug that in. Right? If you have already this formula for position as a function of t, all right, well, if t is a function of s, stick it on in there, and now you've got position as a function of s. Right? So this is how you perform the reparameterization. You compute the relationship between distance and time, and you plug in. Okay. All right, so why would we ever want to do such a thing? There are a couple of nice things about arc length parameterization. In fact, let me come up to here. The first point here is intrinsic to the curve. That's pretty cool. You think about it, there's lots of parameterizations. Which one is the natural what should be the default, most basic fundamental parameterization? You can make the case that parameterize the curve by something that you can see on the curve, and how far I have traveled from the fixed base point. That's it's intrinsic to the curve, right? So another way to say this is if you look at a road again, and you're driving, different people driving down the same road, who should you pick? Whose path should define the parameterization of that road? Well, nobody is naturally. They are not part of the road, right? But the mile markers are. The mile markers stay there. They are natural, and it's got nothing to do with the drivers. So that's that's worth something. There's another really nice thing about arc length parameterizations. And that is that they actually move at unit speed. The velocity of an arc length parameterization is always 1, and it's an easy little argument. Hard to see it coming, but easy to follow. There's the chain rule. Right? Position's a function of s is a function of t. Write down the chain rule. Here it is. And then notice that if you take the magnitude of both sides, the magnitude on the left here, well, that's the, that's the magnitude of the velocity vector. That's known as speed. This thing here, distance per unit time, also speed. So these two things are equal. That just kind of turns out really nicely like this, and therefore this is therefore 1, and that's why we say it's a unit speed. The speed of as your position changes with respect to s, change in position with respect to distance has velocity 1. So yeah, that's also kind of cool. How much is this worth to you? It depends on the circumstance. To be totally honest, it's usually when you're proving theorems that arc length parameterization is particularly useful. And to that point, that brings me to number 3. Unfortunately, it's usually a pain to parameterize by arc length. And I'm just going to show you an example. Now, this is not the easiest example possible. There's a very narrow category of what I will call reasonably easy examples of doing arc length parameterizations. As already noted, you're going to be taking an integral of a square root. It's usually going to be a bummer. Now, here I have crafted very carefully, very strategically. If this is your position, well, then you can talk about what the velocity is. The velocity has these coordinates, which if you square that out and kind of collect terms, notice that this 4 tau squared is going to kind of basically turn that minus into a plus, which is going to make it a perfect square under the radical. This is a very carefully manufactured, artificial kind of example. But wonderfully and amazingly, that square root goes away because I was very careful again when I manufactured this example. So you can actually work out this integral much more easily than you normally can, and yet it remains that the resulting relationship between s and t still annoying. It's cubic, right? So how do I solve for t in this equation? I don't really know how to do that, right? So, like I say, notoriously hard to actually arc length parameterize a curve, but important to know what it is, that it exists, and that it has nice properties. Okay. All right. So, moving along. I'm going to introduce a new mathematical object here called a vector field. You may have seen vector fields before. Maybe not. You almost certainly have seen the discussion of something that is a vector field, but perhaps maybe not presented in those terms. So, first of all, what is it? A vector field is a function that takes every point, right? So, what goes into the function, the x here is going to be interpreted as a point, and then what comes out will be interpreted as a vector, which I'm going to represent, as usual, of course, with an arrow, but specifically an arrow whose tail is at the point that gave rise to that vector. Okay, so this is the big idea. It's again, algebraically we write it as a function, but intuitively or geometrically, the way you think about a vector field is at every point, at that point, I should think of there being a vector representing something that's happening at that point. Now, here I drew a two-dimensional example. Of course, there's just as easily, you can talk about a three-dimensional example. At every point, there is a corresponding vector. So, what an odd little construction to manufacture, you might think. What does this have to do with the real world? Where am I going to use this? All reasonable questions. And I'm going to point out a couple of really good answers before we move along. I tell you what, when I look at these pictures, I see wind. Right? In fact, now that I think about it, today being a hurricane day, I have an app on my phone that literally shows what the wind speed is. It's kind of cool. You can really see a sort of a picture of the hurricane, right? And they literally draw little arrows representing what the wind velocity is at each given point. So that's a live, continuously updating vector field on your phone. So that's pretty neat. So so there's a very natural application, very natural, you might say, manifestation of vector fields in the form of how wind blows, how fluids flow in general. But there's another one, and that is forces, right? So it could be that due to where certain electric charges are placed around in space, there's at any given point, there is an electric force. What is the electric force that those charges are applying at any given point? Right? So a vector field could represent forces that come out of a positioning of electric charges. Or likewise, it could be gravitational forces that are created by the positioning of certain masses. So either one of those could be. So not wind, and it does not have to always be a fluid flow. It could be something like electric forces or gravitational forces. All right. So we're going to see some examples here. I'll start with this example here, an easy first example. This says at every point x, y, the vector field, the field vector, the output vector for that point is 2, 1. So here you go. For that point, it's 2, 1. And the thing is, this is true no matter what x and y are. So for this point, different x, y, notice the field vector, still 2, 1. And so you get this picture here where all the field vectors are pointing exactly the same. So this is what we call a constant vector field. Does that make sense to everybody? Oh, here's another thing I should say. These pictures we're drawing, yet another kind of picture that we're drawing that's not a graph. So just a reminder, heads up. So we have, in our collection of different kinds of geometric constructions to represent functions. We already had graphs, level sets, parameterizations. Really, there's a picture you associate with a function, and then one of my favorites, the unsung, the literal interpretation of the function. Right. So we already had 4 different kinds of pictures. Calculus looks different in all 4 of these pictures. And now we have a 5th, and that is the kinds of pictures that we draw to represent vector fields. And the calculus of these kinds of pictures is totally different from that of the previous 4 that we've already seen. All right. Is everybody with me? So don't make the mistake of thinking, oh, well, this is a constant, so the derivative is 0, so all these lines should be flat like that. No, that's graph thinking, right? And that just does not apply in these pictures. Okay. All right. Here's the next example. Looking over here at this example, notice my formula is an eyebrow raiser for any given point. There's my point. The field vector is, I'm going to say it's the same, but we have to be careful about this because, of course, the input is interpreted as a point. The output is to be interpreted as a vector. So they're not exactly the same, really. Right? What they are is that the field vector is the vector that corresponds to this point, aka it is the position vector of that point. But of course, our convention is to draw field vectors such a way that their tail is at the point in question. So we draw it like that, right? But where did this vector come from? Well, it came from, it's the position vector for the point we're at. Okay, what do you think? Everybody okay with that? And I note that if you do that for a collection of points, then you'll get a picture that looks kind of like this over here. The field vectors always point, as per this example, they always point away from the origin, radially outward from the origin with magnitude equal to, however far you are away from the origin. So the further you get away from the origin, the longer the field lines, the field vectors are. What do you think? Okay. Cool. Yes?
So at 0, there should just no.
At 0, no, there is a vector there. The vector is the 0 vector. Yep. But there's yeah, that's right. Yeah. Yep. All right. There we go. Okay, here's a weird one. This is where we're going to use a little bit of linear algebra, so I'm going to remind you that we already know a relationship between x, y, and negative y comma x. And so think back to linear algebra and matrices, etc. I claim that this field vector is just a quarter turn counterclockwise of the position vector. It's not xy, obviously, but if you rotate the position vector xy quarter turn counterclockwise, you will get negative y comma x. And so the position vector xy is that. Rotated a quarter turn counterclockwise gives you that. Green. It's supposed to do that green. Gives you that. But of course, we don't draw field vectors emanating from the origin. We draw them as emanating from the point where we're evaluating the vector field. And so we get that picture there. And again, repeat that, at various points, and you'll see we get this kind of, again, I tend to think in terms of fluids, right? And so this looks like a stirred fluid, right? I suppose today being today, it looks like a hurricane, doesn't it? Okay. All right. So just another example. All right, now here's a really important example physically. This is the formula for the vector field representing the gravitational acceleration that comes out of a mass. Or likewise, the acceleration due to electric forces coming out of a mass. So we call this, therefore, a gravitational field. Or, if you're applying it to electric forces, then this is the electric field. So y'all heard gravitational fields in any science fiction movie you've ever watched, right? And you've heard of electric fields. Well, it's just literally representing what the forces are whatever point you might be happening to look at. So structurally or mathematically, what we call these radial inverse square vector fields. The radial part, I think, is pretty easy to buy because the vector direction, wherever you might happen to be, wherever your point is, the direction that it's pointing is, it's again the direction of the position vector. So it's always going to be parallel to the position vector. It's therefore always going to be parallel to a radius, literally a radius from the origin. So that's the term radial. Why do we call it inverse square if the formula clearly has a cube in the denominator? That's a pretty good question. And the answer there is you have to realize one of those is actually doing a different job. One of these factors in here is needed to turn the x vector into a unit vector and to therefore only define a direction. Right, so there's a hidden factor of magnitude of x that's up inside of this x vector that you might say, if you want to, cancels with one of those three. So, so I'm going to think of it as that's the radial part, and this is the inverse square part. Is that cool? All right. So yeah, very important because, again, gravitational fields, this is what they look like. This is the formula for gravitational fields. And likewise, this is the formula for electric fields. So clearly a big deal in engineering, yeah.
So for electric fields, usually when we draw them, the arrows are pointing out if you have
Yes. So I only drew one here because I just only wanted to have the one picture. Whether it points in or out depends on what this C is. Okay. Right? So I basically drew a picture of a gravitational field, and gravity, unfortunately, philosophical debate, always toward. Right? But you're quite right. Electric fields would be pointing the other way. C would just be positive, and it would look just exactly like this, but with the arrows going the other way. Yep. Good observation. Anybody else? Okay. Yeah. Okay, so here is an example of a vector field that you have seen in this class. But we kind of never really talked about it as such, and that is gradient vectors. And first thing you might think is, well, yeah, but the gradient's just a vector. Well, at a given point, yes, right? So at a point, x comma y, like right there, you are right that the gradient is a vector, and there's the formula for how to compute it. But if you think about it, having a formula for how to compute a vector at any point x comma y that you might happen to be looking at, that formula, because you can do it anywhere, it does in fact define a vector field. We had no need back in chapter 2 when we were studying gradient vectors, we had no need for thinking about all the gradient vectors all at the same time. We were just focused on, okay, I'm at this point. I am here. Therefore I don't care what's happening over here. Right? I'm here, very myopic, and I just want to know what's happening right here, and this one vector tells me what's happening at that point. So, so we open our minds, we think about them all at the same time, and we have ourselves a vector field. So I'm going to revisit an old known fact, and that is that we already knew that the gradient vector points uphill on the graph. Right? That was one of our first interpretations. It points, as y'all recall, I prefer to think of this as the gradient points in the direction of fastest increase. But, more commonly, the gradient is thought of in terms of what if I were looking at the graph of the function, and then the gradient points in the direction of steepest ascent, aka it points uphill. And you can see that in this example. I think it's nice to get the consistent. It tracks with the following picture, which is that here's the graph. And here's the gradient. And y'all can write down the equation of the graph and confirm that I drew the correct graph here, at least within my artistic abilities. And y'all can take the gradient, and y'all know how to plot this gradient. Y'all know how to make a picture of this gradient, because whatever your xy position is, the field vector is just 2 times that. So you can draw that picture, and you get this picture down here. And notice, as we already knew would be the case, these vectors always point uphill, wherever you might happen to be. So, for example, if you are looking at this point, on the graph, again, as usual with graphs, I'm going to conflate the point on the graph itself and the point in the domain that gives rise to it. At this point, whichever one you want to think of, the gradient vector is pointing in the direction that takes you uphill on that parabola. Okay. All right. Now, there's a little bit of terminology to be discussed here. I'm going to use my position as instructor to tell you the one I like best first. So here's the action of computing a gradient, right? So it takes a function, gives us a vector field, and the thing that comes out, being as it is the gradient of the function you put in, I think it's pretty reasonable to call this the gradient field. Right, so we'll call it the gradient. Sure. I mean, of course we would. Of course we would. Why wouldn't we? I'm going to say almost equally naturally, think about derivatives and antiderivatives, right? The thing whose derivative gives you some output is called the antiderivative, and likewise, I think that this function here should be called the antigradient of that vector field. And just like with derivatives, it's not unique, and so we should call it an. Oh, look at this. I wrote the. I'm going to change that. This needs to be an antigradient of the vector field. So I think that's pretty natural and pretty satisfying. Again, just a complete copycat, complete rip-off of the terminological strategy of derivative and antiderivative. Same ideas. Okay. All right. So now with that pitch made, right? Hopefully I've biased you in the direction I like. I have to tell you that you're going to hear other language used to describe the antigradient. So it's very commonly called the potential function. Now, the reason that it's called the potential function is because there is a relationship between potential energy and the vector field, for example, that might represent a force. So if you have a force vector field, called force field. It's again not a sci-fi reference, but if you have a force field and you want to talk about the thing whose gradient is that, well, it is very closely related to potential energy. The problem, and the reason I don't like this terminology, is that it's not potential energy. It's specifically the negative of potential energy. I mean, the point here, by the way, is very simply gradients point uphill, forces pull downhill. It's as simple as that, right? That's the nut of it all. So we do get this minus sign if you want to relate potential energy and force. So anyway, this minus sign, I think, brings this terminology here into question. Is that really a good choice? Of course, again, there is clearly a strong connection there, and that's why I understand their motivation. But when there is a perfectly good alternative terminology here, why bring up something awkward? That's my take. Also, I think this is another really good point. Very often when we're talking about math and gradients and stuff, very often it's not physics, right? So why would we use a language that is peculiar to one example of the mathematical relationship that we're seeing here? So anyway, I'm not a fan. You're going to hear me say antigradient in the book and in other books and in other classes where you apply these ideas. You will more likely hear the word potential function. Okay. Questions? Okay. All right. Okay. So we've already talked about a couple of real-world examples, manifestations of these things. We talked about forces, gravitational forces, electric forces. And I also kind of mentioned that, but it could also represent the flow of a fluid, and there's lots of fluids that flow. We can talk about how air is flowing in this room, perhaps, or out than the hurricane. We can talk about ocean currents. That's a flow of a fluid, right? Pollution, how that moves around. It's a kind of a fluid in a sense. And et cetera, and different. Where's the ozone? How's the ozone moving around in the atmosphere, et cetera. And that's three-dimensional examples. You can also talk about two-dimensional examples. Surface water being a sort of an obvious one. Again, today the water is going to be flowing around, and how is it flowing at any given location? I like to point out that animal migrations can also be thought of as a two-dimensional vector field, because we don't think of animals as being fluids, but they kind of are. In a sense, so just to make it a little bit more clear, if you have a glass of water, we think of that as a fluid. That's a bunch of particles. It's a bunch of particles that relate to each other. Some of them start moving, and the rest of them kind of have to move along with them. And frankly, so is a herd of animals. If you have a bunch of wildebeests, a great big herd, and they're flowing around, they flow together, right? By and large. Okay, so lots of examples, lots of applications, broad fields of application. Okay, so I'm going to do a calculation here. I'm going to phrase as a question, and it's going to turn out this is going to lead us to a very important concept. So this is a motivating example, you might say. So suppose you have a vector field, and in particular, I'm going to pick now the interpretation that we're taking. Does my vector field represent forces? Does it represent the flow of a fluid? Which is it? Specifically here, this vector field I want to talk about represents the flow of a fluid. And more specifically, the vector field is telling you at a given point where you evaluate it, what is the velocity of the fluid at that point. Right, so that's my vector field. I want to understand how the fluid is moving at any given location, what's its direction, and how fast is it moving in that direction. Is everybody on board? Okay. So with that information, a reasonable question I could ask is, what's the flow rate? How much volume per unit time is moving through some piece of area? And so, for example, here's a piece of area, and we're going to start off here in Chapter 3 anyway. We're going to talk about a small, flat, very importantly, small and flat piece of area at a given location. And if the fluid's flowing around, and again I have a vector field here representing velocity, and if that vector field is doing like this, that means that the fluid is doing like this. The fluid is passing through that piece of area. Very reasonable question is, how much volume per unit time? I mean, there's an amount of volume, right, of whatever this fluid is that has passed through that area in a given amount of time. And given the vector field, I would like to know, given the vector field and given the area, the small, flat piece of area, how much volume is flowing through there? We'll get to the calculation in a second, but does everybody understand the setup and the question? Yeah? Okay, so for example, maybe you have a screen door on your window. Not today, right? But if you had a screen door on your window and you opened it up and you're getting some flow of air through there, you can measure the velocity of the air coming into your window. But you also would naturally be interested in, how many cubic feet of air per minute am I getting to flow through here, right? And so that's the relationship we're looking for. All right. So the way we're going to answer this question is a very brute force calculation. In some amount of time, delta t, we'll deal with what that is in a minute, but in some amount of time, delta t, here's the fluid that has flowed through my area. There it is. There's a picture of it. I need to know, first of all, how much volume of fluid is that? And flashback to high school geometry. But this height times that area. Height times area gives you that volume. Yeah? Everybody remember that whole geometry formula? Okay. All right, height times area. What is the height, though? That height, I mean, how it's tempting to say how far did the fluid get through, right? But you don't want to conflate that height with this displacement vector representing the actual, this is how much the air actually moved. Because the air might be moving kind of at an angle. It might not be moving straight through the area. Right? It might be moving off at some angle. So that being said, okay, well, nevertheless, I can compute that. It's just going to be the component of that displacement vector, specifically the component in the direction perpendicular. It's literally the perpendicular direction that I care about because, again, height being perpendicular to the base. What do you think about that? Everybody okay? Keep in mind that normal vector given to us as being perpendicular to our little piece of area. Okay. All right. So what's that displacement vector then? Right? We've got this displacement vector representing how much the air moved in some given amount of time. Well, that displacement vector... Oh, sorry. Got a little ahead of myself. Quick observation. Components, we have a formula. Dot product. Right? Specifically, n is a unit normal vector. And so I don't have to divide by anything. Right? Unit vector n. That's an important thing to keep in mind. I mean, when you're writing a normal vector to represent a piece of area, we do need it to be a unit vector so that we don't have to deal with additional constants here. Okay. And now then, what's that displacement vector? Well, displacement is velocity times time. And don't forget, our vector field represents velocity. Everybody okay with that part? Okay. So we're basically done, actually. Just a quick reminder, we were interested in computing the flow rate, volume per unit time. What we've computed here is we've computed the volume. So we're just going to then divide by whatever that amount of time is. So I'll cancel that delta T, right? And what's left over... the answer to our question, the flow rate, dV dt, is, again, just what's left over, and it's this formula right here, F dot N times the area. This is an expression that's going to come up a lot, so it's worth having a name. The name is flux. There's different interpretations of what flux is. The one that I want to use here is that it represents the volume per unit time of fluid passing through a given little piece of surface. Okay. Everybody on board? Okay. All right. Now, here's a related question. And I want to start with reminding you what we just addressed. We just addressed the question of if your vector field represents velocity. Okay. Now, separate question though. What if your vector field no longer represents velocity? What if your vector field represents density times velocity? And that seems like an odd little thing to throw in there. Why would I be interested in density times velocity? Well, a quick case that I could make just for, kind of intuition purposes, if you standing there and there's a 7 mile per hour wind hitting you in the face, right? That's a gentle breeze. It's pleasant, and it's not going to knock you over. But if you are in a river trying to stand there, and there is a 7 mile per hour flow of water hitting you, you're going, right? It will instantly knock you over. You can't begin to resist that amount of power, right? So the velocity is not the whole point. If it's dense, like water, that's a lot more of something. It's more of something, right? So factoring in the density actually is a pretty natural thing to want to talk about. And I'm going to leave the following as an exercise to y'all. It's going to be a nice sort of test of the extent to which you understand what happened here. It's going to follow this calculation almost exactly. But how would everything be different if we were interested in mass per unit time instead of volume per unit time? And get 2 seconds. And the answer is going to be, if you're computing mass per unit time, well, instead of starting off by looking at the mass that has passed through the surface, instead of looking at the volume like we did here, you're going to look at the mass that has passed through, and the mass is just density times volume. Right? But anyway, you write down the mass, do the analogous calculation, divide by delta T, and what you're going to find is that volume per unit time here ended up being flux. Mass per unit time, well, I'm going to do it like this. Mass per unit time, in this case, again, flux. It's that same formula. So, arguably better answer to the question of why would we want to multiply density times velocity? Well, because that's what you have to do to have this agreed upon, useful expression called flux interpret something natural, namely mass per unit time passing through a surface. Okay, you had a question. I'm sorry.
You already answered.
Oh, okay, perfect. Okay, all right. So that's where we got to end it for today, and see y'all on. Let's see, what's today? Today's Friday. Oh, yeah. So have a good weekend. Stay dry, hopefully, dry and safe, and see y'all on Monday. Have a good one.